Hello, my name is Sean Stevens,
And I'm Kyler Palmer.
and we're going to be going over Ohm's law and Fourier's law and their relationship. Okay, let's get started. Here's a overview of what we're going to be going over, and it kind of shows the map of how we're going to talk about things. We'll start at Ohm's law here on the right and discuss this relationship, and then go into the Ohm's law power derivation here, and then we'll see how that relates to Fourier's law here, and then we'll see how Fourier's law relates to the resistance, the electrical resistance of material here, and get back to Ohm's law. Yay!
So we'll start out by talking here about Ohm's law. And Ohm's law is really a relationship of the voltage and the current through any electrical element that you have. So you use a battery or some other source of electrical potential to put a voltage across your circuit element, and what happens is that a current will flow through your device, right? So we can measure that, and experimentally a lot of people have measured that. And what's it end up looking like? If we graph the relationship of the voltage across this device to the current through it, you probably remember that it results in a line, which is the voltage current relationship, and this slope here is the resistance of the device. And what that means is that there's a linear relationship between the voltage and the current, and that's something that people have known about for a long time. Nothing new here. We say nothing new here, but we might want to look real quickly at why there is a resistance in the material. Why doesn't a current through this device just pass through with ease, and what causes it to slow down? So as you can imagine, in the wire or device that you're sending this current through, there are lots of atoms, and all of these atoms in a metal, they're just kind of floating around, hanging out as close to each other as they can be. And electrons are going to flow through here. So if we have a little electron, we'll make him green. The electron is going to try and flow through here, but he's going to run into somebody, and he's going to bounce off in some other direction and then run into someone else. And he'll slowly, make his way in the general direction that is dictated by the voltage, as we've learned before. So if you have a voltage across this, he will, in general, flow opposite to the direction of the electric field created by this voltage.
Okay, so here we have the electrical power relation between current and resistance, and so also important to know here, P equals VI, but we know through Ohm's law that the voltage is the current times the resistance, so that's where you get this from, I guess V equals IR, and then you just substitute this IR back into the equation here. So what's important to take out of this is that the amount of power dissipated within a material, P, will increase as R, the resistance of the material, increases, which will be important when we come back to relate how Fourier's law will relate to Ohm's law later.
And now we have arrived at Fourier's law. And Fourier's law is really similar to Ohm's law. You can just look at it and kind of tell. Well, it's convenient that we've named something R, just like in Ohm's law, the resistance is named by R. We have a thermal resistance that is here, and it relates the change in the temperature of your material to the amount of power that's being dissipated in your device. And so you can imagine that this, just like Ohm's law relates a current, a change in voltage to a change in current, Fourier's law relates the temperature change to the power change, and it's a linear relationship. And the slope here is the thermal resistance. So you can tell that these are really, really similar as far as the math of them. So this thermal resistance is basically a resistance to the flow of heat through a material. And you can imagine that as energy is dissipated through all of those collisions of electrons with atoms that we talked about, the temperature of the material will rise. Energy is being added to the system at a specific point, and so the temperature through the vibrations of atoms and the movement of electrons is going to slowly move through the system. So the important thing here is that temperature will rise with power being dissipated in the system.
So with Fourier's law stated, we can now look at the relationship between the resistance, the electrical resistance of material, not the thermal resistance, difference between R and RTH, I guess, and the temperature, the change in temperature of that material. So, and this one is kind of similar drawings to the power relationship, I guess. You'll take the electrical resistance of a material will increase as the temperature of that material increases, and this is due to an increase in the scattering of the electrons as they move through the material. So if we see our little atoms here in red, like Kyler said earlier, they'd like to be as close as possible to one another. As temperature increases, they're going to vibrate more, and the distance of these vibrations is going to increase as well, which means an electron, finish drawing those, an electron traveling through here is going to encounter more atoms as it's moving through. So the higher the temperature, the more more vibrations, the more collisions, the higher the resulting resistance.
So now let's look back at the loop that we looked at for our first slide there, and let's look at what we've done. We've followed Ohm's law and looked at how that relates to power. So a resistance in a material causes an increase in the amount of dissipated power, right? If you have higher resistance, more power is dissipated. And then we looked at Fourier's law. If more power is dissipated in a material, a larger change in temperature will occur. That makes sense. And then we can follow that around, and we looked at how sort of the lattice vibrations of a material will cause a larger resistance to be encountered by electrons if they're flowing through that lattice. And now, if we have a larger resistance, what happens? It will affect the voltage that's encountered by the same current. Or, if we follow it one step even further, a higher resistance results in more power. So we can see this is just going to cycle around and around, and you can't escape from the fact that Fourier's law and Ohm's laws are coupled to each other, and one will affect the other in any material that electricity flows through.